Our topic for today is the integral test. So let's state the theorem and then see how this theorem can help us to decide questions about convergence of the series. So theorem. If f is positive, continuous, and decreasing, on the segment 1 to for x greater equal 1, then the sum n goes 1 to infinity f of n and the integral f of x dx between 1 and infinity are equiconvergent. What is the meaning of that word, equiconvergent? That means they have the same convergence behavior. If one of them converges, the other one converges as well. If one of them diverges, then the other one also diverges. So that's basically the theorem. We'll see a proof in a moment, but let's see first why is this useful theorem for some applications, and it will help us actually to make some conclusions that otherwise we wouldn't be able to make so easily. So generally the main flavor of this theorem is actually that we have much better ways to assess this question, because integrals are much easier, thanks to the fundamental theorem of calculus. Integrals are much easier very often to calculate and then to assess their convergence than finite sums and their limits. So usually we use it analyzing integral and improper integral though, and making conclusion about the series. By the way, that's one of the main reasons why we studied section 8.8, because that's where these integrals showed up. So here's example. Sum 1 over n equals 1 to infinity. By the way, this is the famous harmonic series. Diverges. How do we know that? Because we are just applying this theorem for the function f of x equals 1 over x. And then on x greater equal to 1, this function is obviously continuous in this segment. It is positive, and it is also decreasing. Why? It's common sense, we don't need any heavy machinery on that. The bigger x is, the bigger the denominator with a fixed numerator, that means smaller fraction with positive numbers. So this is very easy to kind of check conditions, because remember, if you want to call a theorem, you have to make sure that the conditions of the theorem are satisfied. So these are conditions: positive, continuous, decreasing. And when you call integral test in your, for example, on the exam, I want to make it sure that you just are aware of these three things to be checked. You cannot just say, oh yes, I saw it. No, you have to demonstrate on your paper, yes, I checked it. Even if it's a trivial argument, like in this case, at least I want you to show me that you are aware that these three things should be checked. And then what? Then let's consider the integral 1 over 1 to infinity 1 over x dx. And that one is, you remember, limit when b goes to infinity, integral 1 over x dx between 1 and b, which would be limit when b goes to infinity. This would be ln x. I don't need absolute value because everything is positive between 1 and b, which is limit when b goes to infinity. ln b minus ln 1, if you want, although ln 1 is 0. And that limit is infinity. Why? Because we know how ln goes. So when when the input goes to infinity, then output very slowly, but goes to infinity. So this limit is infinity. So then, what's our conclusion? Then we would write a sentence. Let me squeeze it in here. Conclusion. Since integral 1 to x, 1 over x dx is divergent, sum 1 over n goes 1 is also divergent. So they have the same steps. That was very easy and actually a very powerful application of our machinery that we developed in 8.8. Let me try now to squeeze in here. Very similar question. I want you to see them next to each other. Actually, I will erase this conclusion because you know what it is. Because I want to kind of compare these two examples side by side. Sum 1 over n squared and goes 1 to infinity. So our function this time is f of x equals 1 over x squared for x greater or equal 1. And the same way as before, we check easily that it's continuous, positive, decreasing. So conditions are met. So instead of analyzing the series, I can analyze the integral. So integral between 1 and infinity, 1 over x squared dx. What would that be? Let me erase this last one. So we checked it. Then the same way as a minute ago, just a little different function. Because integral from 0 to infinity, 1 to b, 1 over x. Just there is an extra power out there, and of course that influences the integral. It's not ln anymore. It will be what? Negative 1 over, this is x to the minus 2, x to the minus 2 over minus x to the minus 1 to the minus 1, so it's minus 1 over x between 1 and b. And what happens here? It's a, let me flip the limit when it goes to infinity. Because of the minus, I flip the limits. 1 over 1 is 1, minus 1 over b. When b goes to infinity, 1 over a huge number is very small, the result approaches 0, so we get 1 minus 0, which is 1. So conclusion now is completely different one, and that is since the integral 1 to infinity, 1 over x squared dx converges, sum 1 over n squared and goes 1 to infinity also converges. Here it is. So generally, you see both sides of the application. So the case when one of them, when integral diverged, and series follow the same trend. When the integral converges, series follow the same trend. Of course, it's reasonable here to ask a difficult question, by the way, and the answer will be very important for us, and that is, all right, so how high should be this power? Because when power was 1, it diverged. When power is 2, it converged. So in general, what can we say about convergence of the series 1 over n to the p? So let me, I'm not going to erase that one. I will just say here, what if it's 1 over p here? where P is a positive number. P is, what can we say here? P is greater than 0. Why am I analyzing only P is greater than, well, actually, yes, because if P is greater than 0, then this will be a decreasing function and I'm allowed to apply it. If P is less than 0 or equal, then it's very easy to see that that has no chance to converge, because 1 over n to the P would be what? If this is negative, then n goes in the numerator, and then according to the nth term test or divergence test, obviously diverges. So the only interesting case to analyze if P is greater than 0. And generally what happened here would be, I'll just write on top of it because you will see that the same thing happens. So this is P. Of course, if P, I can do this, so 1 over x to the P. And then integral of x to the P, if P is not 1, because P equals 1 is here. If P is different from 1, it will be negative 1 over x to the, or it would be what? So this is, I better finish it on its own. So I'm just repeating the same analysis in the general case. So that would be what? Limit when b goes to infinity. This is x to the minus p, so it will be x to the 1 minus p over 1 minus p between 1 and b. So what would that be? It would be a limit when b goes to infinity, 1 over 1 minus p times, this would be what? B to the 1 minus p minus 1. And then what could happen? Now what? If p is less than 1, because p equals 1 was already analyzed here. If p is less than 1, then what happens? 1 minus p is a positive exponent. So we have infinity, be a very huge number to the positive, the exponent. So it will go to infinity. So here I go. So it goes to infinity if p is less than 1. What if p is greater than 1? Then 1 minus p is negative. When you raise infinity to the negative power, you actually get a reciprocal of infinity, which is 0. So generally converges, doesn't matter. Oh, actually we can even calculate it. It's 1 over p minus 1, because this converges to 0. Why? Once again, we are raising infinity to the negative power, so it's 1 over infinity, which is 0. 0 minus 1 is negative 1, so we get 1 over p minus 1. So what do we conclude about our improper integrals? If p is less than 1, it diverges. If p is greater than 1, it converges, and then p equals 1 is here. So generally, here is our p-test. It's very important because that's 1 over n to the p will be our measuring stick. So let me erase now all this and just formulate this. Or actually erase everything. So, like a p-test. It says sum 1 over n to the p, where n goes 1 to infinity, diverges for p less than or equal to 1, converges for p greater than. This is a very important test. Why? Because as I said, very often you will see that in our next section, others, more complicated series will be compared with this one. So it's very important that we know this, so that we don't mix it up. Actually, if you use common sense, you shouldn't mix it up. Why? Because what? The higher P is, obviously, the heavier denominators, and that means drops are smaller, so more chances to converge. So if p is greater than 1, then it will converge. If p is less than or 1, it diverges. I forgot a minute ago, by the way, to make a couple of comments while calculating this. What is it? Sum 1 over n, that's harmonic series. What happens there? You remember a minute ago, we say diverges. Even 1 over n individually, members go to 0. So generally, this is the example of the series that passed divergence test, but still happened to be, at the end of the day, after finer analysis, it became divergent. So that warns you about not jumping to the conclusion if a series passes divergence test that it's gonna converge. No, there's a long way to analyze things. Well, they'll just specific name, sum 1 over n squared, that's convergent. This one is called hyperharmonic. Just traditional, if someone uses the term, this is hyperharmonic because it's squared, so it's kind of that's what that hyper word refers to. Is squaring, and those are probably the most famous series and very important for our future analysis. So basically that's what it is. This is what the integral test is. Once again, making sure to remember the conditions and then how to apply. What we'll do now, we'll just analyze this in a little less trivial situation, but generally just as long as you can calculate the integral and if conditions are met, then this will work. Usually when we have a section, we advertise certain technique. Don't think now that this integral test looks very good and elegant and all that. Don't think that that will solve all the problems that we do. Generally important assumption is that that function that you analyze satisfies conditions, and also that integration could be done nicely, you know. So if integrals look strange, then probably you're not gonna use this test, and you'll see we'll learn a few other tests along the way. But let's illustrate this one once again. So, actually before I give you more examples and we practice more calculation, let me give you the proof. We don't have to insist on all the details of the proof. I doubt that I'll ask you to prove that, but there are a couple of reasons why I want you to see this proof, because this proof will also be the basis of the error estimate that we'll do a little later on. So here's the proof. So here it is. So assume first that conditions are met, of course, and that integral 1 to infinity f of x dx converges. And basically what we'll do, we'll compare our integral and the series. And how are we going to do it? So here is 1, 2, 3, 4, and so on, goes forever. So at 1, our function has some value, whatever it is, and then our function is decreasing, it doesn't jump, so it goes like this, okay? It should approach 0, otherwise you cannot have convergence. So generally, this assumption says that all this area, infinite area, is finite. This infinitely long area is finite. And then here is how our series will come into the game. There is a way to represent series using the area. What is the idea? That series has the values f of n. So f of 1, which is our first member, is this. So this is f of 1. It's just this stick. I calculated it at 1, and then I calculate, here is f of 2, here is f of 3, here is f of 4, and so on. And and those are just lengths. But here's a very intelligent way, instead of length, to actually consider the areas. Why? Because look at this f of 1. I will draw a rectangle with a base of 1, so here is a rectangle. That rectangle has area 1 times f of 1, because base is 1, which is just f of 1. So area of this rectangle is f of 1. The same way, but we stretch to the left. This is area f of 2. This is area f of 3. This is the area f of 4, and so on. So now we will say the following. Our sum, f to the n, when n goes 1 to infinity, is equal. This f of 1 I will just put separately. Plus, and then f of 2 plus f of 3, and so on. I should put a limit here and everything, but I think intuitively it's all clean if you write it like this. And then it's less than or equal, f of 1 is just f of 1. Look at all these areas together, f of 2 plus f3 and so on. So f1 is here, so that's already taken into account. Look at these f2, f3, f4, f5. If you compare these rectangles with my area under the integral, obviously that sum is less than or equal than integral between 1 and infinity f of x dx. And here is where it's crucial that function is decreasing. So because what? You see here in this stripe, when I calculate integral, I take the heights all the time in the Riemann sum. But when I do the series, I calculate the value at the end. So height at the end, which is this red, is all the time below. So generally, a red zigzag line is always below the black line, exactly because of monotonicity. That's why it's crucial that this is decreasing. And then, of course, I cannot play that game with the red one because I'm not using, but one number doesn't matter. And then what? This converges. So our sum, f of n, is limited or bounded. So if it's bounded, then it increases because I'm adding positive numbers. So basically what? We can say partial sums with more precise argument. Partial sums, Sn equals sum I equals 1 to n, f of n, are bounded. And that's what we showed here, bounded by the integral plus a number. And they are also what? Increasing. Why are partial sums increasing? Because each time I add an extra positive block, so they are increasing. So according to our theorem from 9.1, limit Sn exists, and that limit is actually our infinite sum. And that's why. So according to the theorem, limit Sn goes to infinity exists. So that means sum an goes to f of n exists. So it is convergent. That's it. That's a proof. And really, I think it's not complicated, and it's a good exercise in all these notions. All right. Now I need to prove the other side also. If the integral diverges, why will the sum diverge as well? And the argument is almost the same. The only difference is I will stretch my values not to the left, I will stretch them to the right. So I will erase this red. So you see how I stretch to the left? Now I will stretch it to the right. So this is my f of 1, stretched to the right. This is my f of 2, stretched to the right. If you stretch to the right, because of monotonicity, your value in the beginning dominates everybody else. So now it's the other way around. My actually boxes, so now these are the boxes. Now they are green. Now what happens? My green boxes are now dominating the curve. Maybe I should even make everything green and forget this so that it doesn't bother you. That was the previous extension. So here it is. So now if you compare green and black, green is bigger than black. And then what do we have? So what I'm doing now, I assume that integral f of x diverges. Then what do? Then we'll say the following: sum f of n, when n goes 1 to infinity. Actually, maybe I should want this to be green because that's the green sum. Those are green boxes together. Is what? Greater than or equal than this integral. Why? Once again, green rectangle is bigger than the stripe because I'm stretching to the right, so value in the beginning is bigger than all the others. So since green is above black, then this is f of 1. F of 1 is bigger than this stripe. F of 2 is dominating this stripe, and in every part they dominate each other. Of course, we're taking limits here, but that's obviously quite clear. So since this is infinite, diverges, then our sum is also infinite. So sum f of n, well, it doesn't matter color anymore, and goes 1 to infinity, is also divergent. So that's the reason why actually we are able to compare one continuous expression with a discrete one. The crucial good idea was actually not to think of the sum as lengths, but to multiply them by 1 and see them as areas, and then they were in the same ballpark, so we would have played the game. So now I hope we see it better why it works, and then let me see one example where just integration will be less trivial, but really nothing fancy. So here it is, example number 4. Determine the convergence of the series sum n goes 1 to infinity and e to the minus n over 2. You know, sometimes it's good when you look at the math problem to just have a feeling what your answer might be. You know, don't trust that intuitive feeling always too much, but it's also good to kind of assess things just looking at them. My prediction is that this will converge. Why? Because look, these are positive numbers, and actually what I'm doing is really I'm kind of borrowing a little bit from our next section 9.4, which is comparison. These are positive numbers, and they are extremely small. Why? Because this exponential increases very fast. This n is really small. So these numbers will become very small quite fast. And that's exactly for positive numbers the question. Do they approach 0 fast enough? And this one obviously does. But as I said, this is all informal thinking. What we're going to do here, since we know how to integrate this, we'll just use the integral test. So use the integral test. Of course, sometimes the same problem could be assessed using different tests, so it doesn't matter which one do you use. This time we want just to illustrate it. So if you want to use the integral test, we have to say, what is our function? F of x equals x e to the minus x over 2. I need to check three things. Is it greater or equal 0 on x greater or equal 1? Is it continuous? Is it decreasing? Is it greater or equal to 0? Yes, that's quite obvious because x is greater or equal 1, exponential is always positive. Is it continuous? Yes, exponential function is continuous, x is continuous, product of two continuous functions is continuous. The hardest thing to check is decreasing. A minute ago it was common sense. Here it's not so obvious why is this function decreasing, but we have a very powerful tool to test monotonicity of the functions, and that is first derivative. So I'll calculate first derivative, hoping that I'll be able to show that the first derivative is a negative or non-positive, at least after a while. So let me calculate first derivative. I use product rule 1 e to the minus x over 2 plus x times negative 1/2 e to the minus x over 2. Let me warn you, the thing that really could be dangerous in this course is if your derivatives are not ready. So that's really something. If you have troubles with derivatives, go back to that activity and make it sure to cover that quickly. All right, what do I do here? I can factor out e to the minus x over 2, and then what do I get? I get 1 minus 1/2 x. And then I analyze this positive negative. Obviously, e to the minus x over 2 is always positive, so I don't even need to put it on the board. And here, what about this expression? It's obviously equal to 0, so 1 minus 1/2 x equals to 0, 1x is 2. So generally what it tells me is the following, 2, and then before 2, my first derivative, of course I don't go beyond 1, because that's where we are interested in. So between 1 and 2, actually what happens, my first derivative of prime x is positive, and then it's negative. So my function is increasing here and decreasing here. So my question is, can I apply the integral test? Technically, the way we stated the theorem, we said that it should be decreasing all the time. Generally, it's good enough, and you can see that from the proof, that actually it's good enough if it starts decreasing at some point. So decreasing for x greater or equal to 2. Then we can apply the test. How comes? Because first one or two members never affect congruence, convergence, or divergence. So what happened on the first member will really, as long as we can analyze members from the second on, we can cut off first members. Say, oh, yes, you affect the sum, the result of the sum, but you don't affect convergence status because that's decided later on. So if it's decreasing for x greater or equal to 2, that's good enough. Even if it was 10, if it was million, as long as from some point on it is decreasing, then we can call the integral test. So how do we apply it then? Then we'll analyze convergence. So we analyze integral between what? 1 and infinity, x e to the minus x over 2 dx. What is this? It's a limit when b goes to infinity, integral between 1 and b, x e to the minus x half dx. What do we do here? That's where we need our knowledge from chapter 8, integration by parts. So u will be x, dv will be e to the minus x over 2 dx. du is just dx. And v is this integral, which is, if you use linear connection, minus 2 e to the minus x over 2. Whenever you are not sure, if you rush that, just differentiate backwards. So in derivative of e to the minus x over 2 will be e to the minus x over 2 times negative 1/2. They cancel, exactly what we needed. And what would that be? It's a limit when b goes to infinity. We'll go u times v, which is minus 2x e to the minus x over 2 between 1 and b. plus, minus from the formula, and this minus integral of 2e to the minus x over 2 dx, and limits are 1 to b. Finally, that integral will be done in no time. I can plug in here. So because of the minus, I'll plug 1 first. So it will be 2e to the minus 1 half minus 2b to the minus b half. What would this integral be? The same way as a minute ago? We get negative 2e to the minus x over 2, and that 2 will be minus 4e to the minus x over 2 between 1 and b. So finally, we get limit. B goes to infinity. 2e to the minus 1 half minus 2b to the minus b half plus 4e to the minus 1 half. I flip the limits again. Minus 4b e to the minus b half. So altogether, it will be limit when b goes to infinity. 2e to the minus 1 half plus 4 will be 6e to the minus 1 half. Let me check my calculation. Yes, 6 also. Okay, good. Looks good. So what would that be? Minus 6b e to the minus b half. And I will split this if this limit exists, so it will be, it's questionable. So it's 6 over square root of e minus the limit when b goes to infinity. I'll try to squeeze it. I'm close to the end of the board. And it will be b over e to the b half. What can I say about this limit? Both expressions are infinite. Obviously, exponential will dominate, so we'll get 0. But if you want calculations, since it's infinity over infinity, we can call L'Hopital rule. Derivative of b will be 1. Derivative of e to the b half is 1 half e to the b half. Now it is obvious that we have now e to the infinity, 1 over infinity is 0. So this is equal to 6 over square root of e. So, what's the conclusion? That this improper integral converges, and because of that, our series also converges according to the integral test. So it might be nice to have a finishing sentence here. So since integral of x to the minus x over 2, 1 to infinity converges according to the integral test, sum n goes 1 to infinity and e to the minus n half also converges. Here's a nice finishing sentence to summarize our hard work. All right, so that's the main stuff about integral test. One more thing, and that thing is actually important for practical purposes, and that is, you saw that sometimes we calculate integrals approximating. It will be the similar question, not calculate. We approximate integrals in the cases where we cannot calculate them fully. And the same thing is very often true for the series. So here's my question. The problem. Yes, okay, so let's estimate the sum n goes to 1 to infinity 1 over n squared with the error less than or equal to 0.1. So this is a topic called error estimate. So what happens? A minute ago, we saw that this integral converges. And we informed p-test, so whenever this exponent here is greater than 1, then these series will converge. So this one converges. But we are also interested to find the sum. And this sum, we know what that result is. We might show it that a little later on in this chapter. But at this point, even if I cannot calculate the sum yet, what we can do is the following. Can we give it a ballpark? Is it like 3, 3.7, 9.5, or so? Can we estimate this sum? And actually, in that estimate, we have a theorem about that, about the theorem, error estimate. So, so what do we mean here with the error estimate? I would like to just add a few members and then cut it off somewhere. So that means, error estimate will say the following. So if f of x is greater than 0, what else? F is continuous. And what else? And decreasing. Correct, equal to 1. And then S equals sum f of n when n goes 1 to infinity. Let me call it here f of I. You'll see in a moment why I'm not changing the letter. Because I will use n for the stopping value. And Sn is sum I goes 1 to n f of I. So instead of adding them all up, I'll just add first n. Then we call that usually Rn, nth remainder is S minus Sn, which is positive by the way, because if we keep going, we'll add positive numbers. It's less than or equal integral between n and infinity f of x dx. And that's the error estimate. So generally, if I calculate that integral, then that will give me the estimate. Why is that? It's fairly simple. It's the same idea as in the proof of the theorem. The only thing is it doesn't happen. Picture will not be in the beginning, it will be at the end. So here is nth member. So you did calculate f of n. But then you skip all the others. So these are the ones you skip. You skip n plus 1, n plus 2, n plus 3. So all those you're just cutting off. But then what happens, like in that proof, your error is basically this. This box, the same way as we did before, because 1 times the value, and then this plus 1 plus 2. So here is your next box, and obviously some of these green boxes, and that's your error. This is your error. This is your Rn. This is your Rn. That sum is less than this black integral that starts at n, and this is what that formula says. So, what are we gonna do? I'll say here, let me, so actually, I don't know, so someone gave me the assignment, so I'm not sure how far should I go, to be honest. But here's what I'll do. I'll say, all right, let me try, let me guess the result first. So if I know how many members, let me take 5 members. So if I know a number of members I want to take, I can easily use this theorem. So if I know n, it's very easy to get the theorem. So if I know n, easy. Why? Let me cut it off at n equals 5. So n equals 5, for example. So what do I do then? Then R5 is less than or equal integral 5 to infinity of what? 1 over x squared dx. What would that be? Integral 1 over x squared, I better limit. Integral 1 over x squared is negative 1 over x. Limits are 5 to b. Let's skip one step. You don't know this. So what would that be? A limit when b goes to 5. And that would be 1/5 minus 1 over b. 1 over infinity is 0. So it's 1/5. I'm not happy. So as I said, if I know n, I can just plug it in and calculate. The question here is, they didn't give me n, they actually told me the result, and n is hidden. So what can we do? Simpler way is just keep trying. The 5 was not good enough. What if I tried 10? 10 would work. Or, and that's probably the simpler way, or really work with arbitrary n and then solve according. So I'll do that. So you can do trial and error, and you can do it on your own. I'll show you how to do that. Get n when we know the error bound, it's called. That's very important for all calculations, because calculation should always be as precise as we need. So generally, here they say, don't make it error less or equal 0.1. So what should I do? I say the following. All right. So I don't know where to cut it off. So I'd say the following. My Rn for n that I don't know is integral from n to infinity f of x dx. So I will calculate that. So that would be the integral between n and infinity 1 over x squared dx. And that would be, so I calculated with undisclosed n. So that would be limit when b goes to infinity. What would that be? The same way as a minute ago, negative 1 over x between what? N and b. And that would be limit when b goes to infinity. I'll flip them again, 1 over n minus 1 over b, and that limit is 1 over n. So I calculated all the possible remainders, and then I said, all right, so what do you want me to do? You want me this to be, did they say less or equal? Let's say less than or equal. Yes. So less than or equal to 0.1. And what does that mean? So if I want 1 over n to be less or equal to 1 over 10, that implies that 10 is greater or equal to 10. So generally what it says, if I want to be within, I should cut it at 10 or later. So if I want to save on my calculation with this tolerance, then I'll say what? I'll say S is approximately S10. And when I calculate S10, so what would it be? 1 plus 1/4 plus 1/9 plus 160 plus 135, 136, 149, 964, 981 plus 1 over 100, which is approximately, I hope I have it. Okay, so it's I think it's something like 155. You check it for me. Or I can actually check it. In one of the future lectures, I want to show you a little bit how to use calculator for the series and how to enter that part out of the menu. So let me double check here, plus 1/9, plus 1/16. 1/3. Yes, it's 1,54976, so it's will be approximately 155. So what do we know now actually? We know that the full sum is, so this value is always underestimated because we are cutting off positive numbers. So we know that our S will be between 155 and 165. Of course, if we want to do it more precisely, then we would need to take more members, maybe to go to 100 and so on. Of course, this gets us into much more serious calculations, so maybe we would need more efficient methods to estimate this.